Okay, I've gotten a few questions on determining overall polarity, so I figured I'd make a video just going over the general trends for determining polarity of an entire molecule. This is based off of things we've discussed in lecture, lab, and the textbook. At any point, please feel free to pause the video and try one of the examples yourself before I go over it. And then if you have any questions, please email me before 9:30 p.m. So one of the first general trends is nonpolar bonds and no lone pairs on the central atom, or atoms. In those cases, we're always going to start by calculating the delta electronegativity for the bond types in the molecule. For CH4, the bond type is CH. So you'll need to calculate this once, and it applies to each of the 4 bonds. So delta electronegativity, carbon to hydrogen. Carbon is 2.5 minus 2.1 for hydrogen. That gives you 0.4. That is non-polar. If each of the bonds is non-polar, and there's no lone pairs on the central atom or atoms, we would consider this molecule overall non-polar. For diatomic molecules where it's the same element on either side, those are always going to be non-polar, because your delta En for fluorine minus fluorine is 4.0 minus 4.0, which is equal to 0.0. If the bond is non-polar, the molecule is overall non-polar. For BH3, boron is 2.0 and hydrogen is 2.1. Alright, let's start with hydrogen. So it's a positive number. So that bond, 2.1 minus 2.0 equals 0.1. That's a nonpolar bond. We have 3 nonpolar bonds, no lone pairs on the central atom. So this is overall non-polar. Let's move on to an example where we have nonpolar bonds, but there are lone pairs on the central atom or atoms. We're going to start the same way. Calculate the delta electronegativity for the bond types. Between phosphorus and hydrogen, phosphorus is 2.1, hydrogen is 2.1, that's 0.0. Those are non-polar bonds. Lone pairs, you can think of them like pure electronegativity. So they're going to cause a shift of electrons towards the top of the phosphorus in this trigonal pyramidal shape. So you would consider this overall polar toward the lone pair. despite the fact that all the bonds are nonpolar. For sulfur and hydrogen, sulfur is 2.5, hydrogen is 2.1 in electronegativity, that's 0.4 non-polar bonds. The lone pair again here is pure electronegativity. So we consider this molecule overall polar towards the lone pair. So that's nonpolar bonds. Let's move on to polar bonds. Plus no lone pairs on the central atom or atoms. If you have this scenario, generally they'll be overall nonpolar if your dipoles are equal and opposite. So same step, calculate the delta En for all of the bond types. Here it's all carbon fluorine. Fluorine minus carbon, that's 4.0 minus 2.5. 1.5, those are definitely polar bonds. I also want to determine the molecular shape. So the steric number here, I have 4 atoms bonded to carbon. Steric number of 4 tells me this is tetrahedral. They're all bonded atoms. Now I can write in my vectors. So they're all 1.5. They should be roughly the same length when I write them. You don't need to use a ruler, but just eyeball the same length. That's telling us that these are of equal magnitude, 1.5, and they're all going in opposite directions. If they are equal and opposite polar bonds, the molecule itself is overall non-polar. Let's try that for CO2. Delta En for oxygen to carbon. Oxygen is 3.5, carbon is 2.5, that is 1.0. Those are definitely polar bonds. The steric number I have 2 oxygens bonded to the central carbon. That's 2 bonded atoms. There are no lone pairs, so that's linear. Now I can add in my vectors. I know that they're both going to be 1, so I need to draw them at similar lengths. They are equal and they're opposite because we're linear. Here we're tetrahedral with no lone pairs squishing the bond angles. We are at the true tetrahedral. All the bond angles are exactly the same. All the bond angles are exactly the same, so they are truly equal and opposite. That means this is overall nonpolar. For SO3, again, delta En, oxygen to sulfur, 3.5 minus 2.5, it is 1. We know those are polar bonds. There are 3 bonded oxygens, 3 bonded atoms. So the steric number is 3. That tells me this is trigonal planar. We're at the true 120 degrees for the angle because there are no lone pairs. So is it equidistant? If they're equidistant, that tells me that my vectors here are all 1 and they're all going in opposite directions. They are equal and opposite. If they're equal and opposite, again, it's overall non-polar. Another type is when you have polar bonds and no lone pairs on the central atom, or atoms again, but now we have unequal vectors that are going in opposite directions. In these cases, we now have to calculate the delta En for each bond type. So this is oxygen and silicone, and this is going to be silicone and sulfur. So oxygen is 3.5, silicone is 1.8. Sulfur is 2.5, and again, silicone is 1.8. So in both of these cases, we end up with polar bonds. But one is more polar than the other. Between oxygen and silicone, it's 1.7, which is higher magnitude than sulfur and silicone, which is 0.7. Again, I need to check the shape. We are at 2 bonded atoms to silicone, so the steric number is 2 again. There are no lone pairs, so I am truly linear, and I'm at 180 degree bond angle. So that means my vectors are going to be in opposite directions, except now they are unequal. My vector towards sulfur needs to be smaller than my vector towards oxygen. The vector of silicone to sulfur only cancels out 0.7 of the vector from silicone to oxygen, so there is an overall slight polarity towards the oxygen. Again, these are unequal and opposite polar bonds. Now, if all the bonds are polar, and there are lone pairs on the central atom, it's going to be overall polar because the dipoles are in the same direction. Again, we calculate delta En. In this case, they're all nitrogen and hydrogen. Nitrogen is 3.0, hydrogen is 2.1. That's a difference of 0.9. Definitely polar bond. They are all going to point towards the nitrogen with the same magnitude. But they're not, so while they are equal, they're not all opposite because the lone pair. So the lone pair now, if we look at the steric number, 4, comes from 3 bonded atoms plus 1 lone pair. That means this molecular shape, instead of being truly tetrahedral, is going to be trigonal pyramidal. Lone pairs pushing bonds closer, and so we are now less than 109.5. We are not truly opposite for the bonds. If we're not truly opposite, it means we're actually kind of going in the same direction, up towards the nitrogen. So the overall polarity is going to go up towards the nitrogen. For the hydrogen and oxygen in H2O, again we're going to calculate the delta electronegativity between oxygen and hydrogen. That's 3.5 minus 2.1. That's going to give us 1.4. Definitely a polar bond. Now if we check the steric number, it is 4. There are 2 bonded atoms plus 2 lone pairs. That tells me it's going to be bent. Because the lone pair pushes bonds closer. And we're not at truly 109.5. We are less than 109.5. That means our little vectors are equal and they're going in similar directions now, up towards the oxygen and those lone pairs. So we would consider this overall polar. You can use similar reasoning for NO2. Delta En, nitrogen and oxygen, 3.5 minus 3.0 equals 0.5. Polar bond. Steric number is 3, 2 bonded atoms plus 1 lone pair. That lone pair tells me that we are bent. We're at less than 120. For less than 120, that tells me that my vectors are not opposite. They are equal, but they're not opposite. They're pointing up towards that oxygen, towards those lone pairs. This molecule is overall polar. Now the last general trend is if you have a mix of polar bonds and nonpolar bonds. You guys saw this a lot in your lab, and there are also, I think, a few homework questions on this. You do the same thing, you just calculate the delta electronegativity of each bond, and generally they're going to be overall polar because the polar bonds win out. So delta En of carbon to hydrogen here, carbon being 2.5, hydrogen being 2.1, 0.4, non-polar bond. No arrow drawn. The delta En of carbon and nitrogen, 3.0 for nitrogen minus 2.5 for carbon, 0.5 polar bond. Steric number of the central atom, which is carbon here, bonded to two things, a hydrogen and a nitrogen. That's two. There are no lone pairs. It's only two bonded atoms. That tells me we are linear and at 180 degrees angle. If I write in my vector, it's only from the carbon to the nitrogen because that's the only polar bond. That tells me that overall I am polar in the direction of the nitrogen. When you have an atom that has two central atoms, if I give you this on the exam, I would ask you to find the delta En for the central atoms, carbon and oxygen. So here, carbon's attached to 3 hydrogens, so I need to calculate delta En carbon to hydrogen, which we calculated on this side. It's going to be 0.4, which is non-polar. So no arrows along the carbon-hydrogen bonds. Carbon's also attached to oxygen, so I need to calculate delta En, oxygen and carbon. Oxygen's 3.5, carbon is 2.5, 0.5. Oh, sorry, that's 1. That's polar. And then lastly we have oxygen on this side. So the oxygen's attached to the hydrogen. We have 3 different bond types in this molecule. 3.5 minus 2.1. That will give me 1.4, and that is polar. So here we're talking about bond types. So now I need the steric number for the carbon and for the nitrogen, or the oxygen. Steric number for this carbon, 4 bonded atoms, tetrahedral, 109.5 degrees. For the oxygen, steric number is 4, but it's made up of 2 bonded atoms, a hydrogen and a carbon, plus 2 lone pair. That tells me this is bent about the oxygen, and we are less than 109.5 degrees. Now I'm going to put in the vectors. None for the carbon-hydrogen bonds because they're non-polar bonds. For the carbon-oxygen, it's going to go towards the oxygen, away from the carbon. And for oxygen and hydrogen, it is definitely going towards the oxygen a little bit more than the carbon-oxygen, because it's 1.4 versus 1.0. Because oxygen is bent, it is not exactly 109.5. The electronegativity is going up towards the oxygen. So the electronegativity of this molecule is going to be in this general direction. We would consider this overall polar. Alright, that's it for the types. Let me know if you have any questions. And I'll see you all tomorrow.